today we'll try to wrap this up. So I just wanted to make a few remarks of things that I forgot to say yesterday. So for the moment, before I continue here, there's there were a few things that I'm not sure that I actually said very clearly, but yesterday, so I might have forgotten to make that clear because I was with an eye on the clock, with a gun in my face, basically. So I forgot something. So the first thing I wanted to say is that this the subsystem relativity. So basically I explained two incarnations of this. First of all, the Hilbert space one using these reduction maps, and then the algebraic one. I guess what I forgot to say is that so we have this APN and then S to R1 and to R1. This is however I called it yesterday. And then we have this picture that, this kind of schematic picture, the system relative to one frame. This here is the system as described by the second frame, so the relational observable algebras of these O's describing Fs relative to R2 for some G. And the intersection here was just, the observables of the system that are already invariant without addressing. What I just wanted to emphasize still is that, okay, I'm not going to explain that in detail, but the equivalence comes about by, this here is at the purely gauge invariant level here. So these are relational observable algebras on the perspective neutral Hilbert space. But if you take the reduction maps, so if you, for instance, now conjugate this here, why not write it? R1 for some frame orientation, then really for ideal frames, this becomes AS tensor AR2, but really that this piece here becomes that one and this piece becomes that one, so meaning that really this piece is going to be local to the system in the perspective of that reference frame, and likewise here. So in that sense, when I mentioned that these algebras, they generate a tensor product structure that you can then write as a tensor product. This is just to emphasize that this tensor product really is equivalent with the one that you also have on the reduced Hilbert space level upon reduction with that map. Okay, and this follows from this reduction kind of theorem that I partially proved yesterday. So that's just to say that the that this algebraic way, this way of describing subsystem relativity, it is equivalent to this Hilbert space combination that I gave you first. So that means AS R1 is local to AS R1 reduction. So that's why this is equivalent. Okay? So that's just to, and yeah, I mean really the upshot here is again that because this depends, what the system algebras depends on the reference frame, so the different reference frames refer to different gauge invariant degrees of freedom when they refer to the system. So that's the discrepancy. Okay. So then there was another remark that I forgot to make, and that had to do with this RAQ, this refined algebraic quantization that I didn't really explain, but the one thing I still wanted to emphasize is, so I was kind of very sloppy from a mathematical point of view when I write. So I wrote yesterday, things like this. Okay, strictly speaking, this doesn't make any sense in when the group is non-compact. Okay? And that has to do with the fact that that really, as we saw in this momentum eigen, with the three particles on the line, you get a momentum eigenstate, a total momentum eigenstate, which is a distribution. And so a more precise way so this is, let me just write not quite kosher. It turns out that at the formal level at which we were operating, we don't really lose anything by doing this kind of sloppiness, okay? So that's why it is kind of okay for what I did. But if you want it to be mathematically a little bit more precise, there is this, it's sometimes called a rigging map. And that takes you basically from, so more precise, more precise is that you say, you take a kinematical state and you actually map it really to a distribution by this pi pn, so really you should flip this around. And then you call this here psi, really. Okay. So, this is also when you can see this a little bit when I wrote down this the inner product. At some point I replaced this here by round bracket phi, but this thing here, strictly speaking, is not part of the Hilbert space. But of course, you can take a Hilbert space element, and if this is part of the dual space, it's still well defined. So you can smear a distribution against the wave function. That's okay. So really, you can rather view this as psi like this, and then phi kin, and here. So I'm writing this in a somewhat schematic way, but you can really think of this here as this actually lies in the dual to a dense subspace of the Hilbert space. So this lies in some B star. Okay, so you have some. So that's why it's called a rigging map. Really, it's only defined. So this eta is defined from some dense subspace of the kinematic Hilbert space, and then you map it to a dual space, so linear functionals, those distributions really. And this contains the kinematic Hilbert space, of course, because kinematic states can always smack from the left on other kinematical states, but it goes into a bigger space. And the way you can write this is basically this is what is often written in this refined algebraic condensation. So for more details, you can see Merrill of 90s. So I just wanted to emphasize that this is the somewhat more accurate way. I mean, to explain this in more detail, okay, it takes a bit more space, but at least that what I did yesterday was a little bit sloppy. But then, so this was here. This is a little bit sloppy, but for our purposes, this is so okay for our sort of informal purposes. And that's because for unimodular groups, we have that pi pn dagger is formally equal to pi pn. So because of that dagger relation, when you write this down in a kind of physics way, the equations you get at the end, you can always make them consistent with this here. Okay? You would just basically have to dagger everything. But it's a little bit annoying because then this map is actually an anti-linear map. So there's a bit of extra tweaks in your head that you have to do to write this down carefully, and that just requires more space. But I just wanted to make that comment overall that what I've done so far is, this is okay when the group is compact. When the group is non-compact, take it with a bit of grain of salt. It's a bit sloppy, but for these informal purposes that I used it for, you don't really make a big mistake. It's just then you can make it more rigorous. It's just a bit annoying that you always keep on track of this. So that was one further remark. And so you don't have to go and correct all your equations that I wrote down or so. I mean, for the reason that I mentioned here, this is okay, but it's maybe sometimes good to keep in mind. So, it has to be a little bit careful with what I did there. And then maybe one last thing is, what I also forgot to say is to contrast this perspectival versus the perspective neutral framework, so it's no perspectives in these names. But basically, one of the core distinctions here is this one works only with the reduced Hilbert spaces, so these, I think I called them, for instance, R2 S relative to R1. It only works with those Hilbert spaces, and it always assumes that these are given by these tensor products, at least in all the formulations that have been developed. So it means, so in general, it misses this pi phys S of G that I described yesterday. Okay? So if you remember, in the perspective neutral approach, when the reference frames are non-ideal, you have a non-trivial projector that appears, and the reduced Hilbert spaces, they lie in the image of that projector. So this way, and this is not part of the perspectival approach. Okay, the perspectival approach, it doesn't have the linking structure of the perspective neutral Hilbert space, gauge invariant Hilbert spaces. So you lack some structure where you can see that this is basically what you should have when there's non-ideal frames. The one thing that you can see is that when the frames are ideal, and for ideal frames, this is the identity, it's a trivial projector. In that case, it turns out that the perspectival approach is actually equivalent to the perspective neutral one. Okay? So the transformations are the same in that case. It's just that for non-ideal frames, the perspectival approach has more states than the perspective neutral approach. And the perspective neutral approach, the image of this is the maximal subspace on which these frame transformations are unitary. So it means in particular for non-ideal frames, this approach has non-unitary reference frame transformation because there's too many states in the space. So this here is basically that. So for non-unitary graph changes. So that also goes in line with the statement I made in the first lecture that the perspective neutral approach is the most radical, gives you the smallest state spaces, smallest observable algebras. This is, I explained yesterday why it gives you smaller state spaces than 3 other approaches. This is yet a 4th different approach, and this is a way in which you see that it has smaller state spaces. Okay? That for non-ideal frames, we take the image of this one, whereas that one is ignored. The projector is ignored. So we have more states, bigger state spaces. And it's really, again, what the projector does is it gets rid of all those states that don't transform unitarily. These are not, this is more, to just put it into the context of these different approaches. And I thought maybe I'll just make that comment. It's okay, and then there was another comment, but maybe I'll get to that. One thing that I also forgot to mention with this cross-product story that I mentioned yesterday. So you have this cross-product. It admits traces, so you can compute entropies, and that was not the only reason why people got excited about it, but it's because in semi-classical states it actually reproduces a generalized entropy in gravity, which is the kind of entropy that is expected to obey a generalized second law, so the second law in gravitational theories. So that's also an important point, and well, depending on how we go, maybe I'll come to that. Okay, so yeah, now let's continue with a few really basic ingredients of phenomenon algebras. So yesterday I told you that regional algebras, of course, we complete regions are phenomenon algebra factors, in fact, in quantum field theory. I have 3 factors. Factors really is a generalization of a finite dimensional notion of really a tensor product structure of subsystem partition. So that's why this is quite important when you want to compute entropies and so on. And now there is another ingredient that we need. So I mean, I mentioned it yesterday already. There was this Hamiltonian for the quantum field theory, the boost Hamiltonian, and it is a so-called modular Hamiltonian. So just to give you a little bit of intuition what that is, it's related to Tomita Kiyosaki theory. But really, since I also want to do some other stuff today, I'm just going to give you scratch the surface of this stuff. So really, when we have a phenomenon algebra A, you can define a Hamiltonian, a modular Hamiltonian, that is associated with a cyclic and separating vector. So the cyclic vector means that A psi is dense. A is dense in the Hilbert space. And a separating vector, separating states is one such that A psi equals 0 implies that A equals 0. So, and modular Hamiltonians are associated with particular states, and whenever you have a state that obeys these 2 conditions, you can define a so-called modular Hamiltonian that is associated with that state. Now, cyclic and separating is a property that you can view as basically giving also mathematical formalization of full entanglement, really. So when I have, at least when I have subsystem factors, for instance, for non-trivial algebras. And the way to see this is in finite dimensions. So you could, for instance, consider a Hilbert space 1 and 2, and I can have now AI to be the full algebra of bounded operators on either Hilbert space. It's also phenomenon algebra, in fact. It obeys all the things that I told you yesterday. And now we can ask, what does it take for? So now we can have some state psi, and you can write it A1, I2 over some bases, and then you have CI1, I2. I1, I2, which are some bases in these 2 Hilbert spaces. And now we can ask, what does it actually require for the state to be separating, for instance? So suppose suppose we have some AI in, oops, let's write A1. So it's an operator that only acts in this Hilbert space. So suppose we have this operator and we want to know for which states, when this is 0, when does it imply that A1 is equal to 0? So for which states is that true? And here, when you look at this decomposition, you know, a priori, of course, here I can have arbitrary coefficients. But really, I mean, this guy is only going to act basically on the first part of this state here. So it's only going to act on this guy. And now you can convince yourself that the only way that this is going to be true is that so that you can necessarily infer that this is true is if the state here is actually fully entangled in the sense that if I take a trace over the second Hilbert space, that it's a full rank state. True for any full rank state. What I mean by that is so as in row 1, let's trace to psi. So if this guy, if row 1 has full rank. Okay. Because otherwise, if it wasn't full rank, of course you can have any bounded operator that only acts on the basis elements in here on which this guy doesn't have support. And you get 0, and the operator is not 0. So, but to necessarily be able to infer this condition here, one needs to have that row 1 has to be a full rank state. Yeah. And now, now we can ask also, what does it take for the state to be, so this is separating. So separating for A1. Okay. And now what does it take? So what is this? So what does it take? For psi to be cyclic. For A1. And so now, so basically, we can now take some operators from A1, or we take all operators from A1, and we act on one fixed state. Of course, now what we can do is we can always modify this part here, but we can't modify this one here. So you can change the coefficients here by doing something to the first part of the tensor product. But in particular, what you need to have is that this state is now full rank on the other Hilbert space in order for this to be feasible, that you reach any state in the Hilbert space in this way by acting on the seed state. Because if I didn't have support on some basis elements, so if CI1, I2 for some values of I2 was 0, so meaning I don't have a full rank here, then there's just no way in which I can recover support on that part of the Hilbert space. Right? So I would always, there's no way that I could, I could reach everything here, but it would always remain restricted to a subspace there, because I'm not acting on that part of the Hilbert space. So in this way, you see, sorry. Yeah.
You're explaining that the property of separating is related to the prolongedness of the state you're considering, but the property of separating is the properties for the fundamental algebra you're considering the state, right? So I'm a little bit confused. Why does the property of separating can be explained only by the prolongedness
by full rank here?
Yeah.
Well, because if you don't have full rank, then so if you don't have full rank, so meaning if there are some I1s such that CI1 I2 is 0, you know, then they will. So I only have support on a subspace of this guy here. Then I can always take a bounded operator, because here now I'm taking the full set of bounded operators. On that Hilbert space, I can take an operator, for instance, that has only support on that part of the Hilbert space of H1 on which the state has no support. So meaning then I get necessarily 0.
What kind of polynomial algebra you are considering?
Yeah, of course. But I mean here I'm very specifically saying I'm looking at all the properties. Yeah. So yes, I mean in general it is dependent on the the polynomial algebra represented on some Hilbert space. It depends on the Hilbert space and it depends on the polynomial algebra. But here in this example, I'm assuming I have two finite dimensional Hilbert spaces. And the polynomial algebras are all the bounded operators here and all the bounded operators down. So it's specific to that case. Yeah. So anyway, so by the same kind of argument, you can convince yourself that it is going to be cyclic if it is full rank for the second factor. Okay. So this is if row 2 trace 1 psi is full rank. So that means in finite dimensions, when I have you know, the fundamental algebras, so I'm using this here also because you know, they're commutants of one another. And if they're the full algebras of bounded operators on that Hilbert space, then I can have a cyclic and separating vector only if the dimensions of the two Hilbert space are the same. So because it has to be full rank in both, and that means it's a fully entangled state. It doesn't have to be maximally entangled in the sense of maximal entanglement entropy, but fully entangled in the sense of having full rank. So, psi H2 cyclic are separating then we must have that H1 is in H2. So in finite dimensions. So anyway, so this gives you a sense that, you know, the cyclic and separating notion of a vector associated with an algebra. In particular, in general, we will be interested in some polynomial factor. So really a generalization of this kind of discussion here. When we talk about cyclic and separating vectors, you can think of that really as being, in some sense, fully entangled states between the subsystem defined by your algebra A and its commutant.
Cyclic property is always satisfied if you consider such a algebra.
No. No. I mean, here this A is not, I mean, I'm just saying it's some phenomenon. I mean, a cyclic property is quite special. I mean, here you see, I mean, I need to have a certain condition to be satisfied, right? So it needs to be full rank on the other Hilbert space, here in this space. So it is a special property. And also here upstairs, I mean, this A, you know, of course, if A is the algebra of the full algebra of bounded operators on the Hilbert space in which this lives, of course, it's going to be cyclic with respect to that. But in general, it will be a subalgebra of that. So just like here, A1 is a subalgebra of the full algebra of bounded operators on the combined Hilbert space. So anyway, so this is to give you a little bit of intuition of what this actually means. And now,
sorry, where did you use cyclic property in this?
No, I only discussed it down here.
Oh, okay.
Yeah. So I'm asking, what does it take for psi to be cyclic for the algebra A1? And then convince yourself that it means that the reduced density matrix of the second factor has to be full rank. Okay. So now for any, so now we're back in infinite dimensions in field theory also, or in general polynomial algebras, for any cyclic and separating psi can associate a so-called modular operator, a positive modular operator, and it's usually denoted like this. So it's a positive operator.
So in the case that you have a non-factorizable Euler spaces like QGG,
Yeah.
how can you check the cyclic and separating properties?
Well, I mean, you can still do it. I mean, it doesn't require that you have a tensor product structure. I mean, you will not conclude things about full rank doesn't here in that sense. It's more complicated, but you can still check that, of course. So, well, you just pick, some Hilbert space states. Well, I mean, you have to look smartly, of course, and then you check whether the algebra that you have, whether that actually is generates a full a dense subspace of the full Hilbert space. And for instance, the vacuum is an example of this. So, so this is also related to the Reed-Schlieder theorem, for instance. So this is kind of counterintuitive property in the Minkowski space. You take no matter how small the region in Minkowski space, as long as it's causal complete, some causal diamond, really, really tiny. Well, you have some phenomenon algebra that acts on it. It's a factor. And it turns out that the vacuum, the global vacuum, is a cyclic vector for that tiny algebra there. So it means just by local operations in that, or at least algebra operations, in that region, you can generate any state in the global Hilbert space, including where at space-like separation something happens. The thing is that operationally, you wouldn't think that those operations would be operationally implementable, where we're doing something here in the small region, and then the moon collapses somewhere. So you can also show that if you do restrict, for instance, to local unitary operations, then you can't do anything at space-like separation. So these are kind of other kinds of algebra elements that would allow you to do this. And so, okay, they shouldn't be operationally implementable, but they are part of the local algebra. So, and okay, in view of time, I'm not going to go more into the details of this definition, but the kind of important thing of this guy is that you can use it to define a Hamiltonian or modular flow on the algebra. So you exponentiate this guy to IS, and here minus IS, so you conjugate the algebra, and then you get again back the algebra. Okay? So it's an say automorphism, and here it's really S in R. So this is the modular flow. Okay, so this is quite a non-trivial result. So this may be a regional algebra, of course. Small phenomenon algebra in your QFT, and then you could use the vacuum. The vacuum will obey these properties, and then you can associate a modular flow to it, and that acts as an automorphism for the local algebra. And now we have that this is a positive operator. So we can take the log of it, and we can just define minus log delta psi. And this is the so-called modular Hamiltonian. Associated with that state psi. And so in this sense, you can view this basically as a time evolution of your algebra as described by this Hamiltonian here. Now, of course, so this holds in general for Neumann algebras. So it's also not specific to the type or anything. You can do this for any Neumann algebra. And now for us, of course, the interesting question is, how is that connected to physical time evolutions? And so now the question is, when is H psi really physical, or if you want, really related to a diffeomorphism in space-time? Or we diffeo really, when does it have a geometric interpretation? Because a priori here, I mean, I haven't made any connection to space-time at this point.
Excuse me.
Yeah.
Shall we construct modular operator in this finite set?
Yeah, you could do that, yes. So in this case, in fact, if you do this for finite dimensions, you can take literally, so you take, for instance, 2 qubits and and you take a maximally entangled state. Then you can actually take the identity operator as a modular operator. Yeah, in that case it would be, I think, yeah, in that case it would be the identity operator. But if you can take more non-trivial examples. So modular operators can be trivial. And so I think for
yeah. Comes from infinite-dimensional property, or
The what, sorry?
the non-triviality of
No, I mean also, so the example that I gave you is, you know, if I take a belt state, then I think, yeah, you would get a trivial modular operator in that case. But you could take some other full rank state that's not a belt state, that is a more non-trivial state, and in general will not have that. It's a trivial operator. So that's just an extreme example. But also here you have non-trivial modular operations. So this is kind of the core question, of course, for us here, and in quantum field theory, of course.
Excuse me.
Yeah.
So to set up the modular operator, and how do you use state information of the state?
Yeah, so I didn't want to go to this in view of time because
please skip.
it's a little bit. This requires more of modular theory, with anti-linear operators and so on. That I would have to explain, which
Okay.
in view of what I wanted to do still today, it's maybe.
But anyway, the point is the operator itself depends on that state.
Yes.
Okay.
Yeah. So that's why, yeah, what I'm explaining here, you some of it, okay, you have to, it's more I'm providing you some intuition for it. I mean, to really understand this properly, it's a lot more work than this here. So, in general, the answer to this is not known. So, I mean, in recent years, there was a lot of discussions about geometric modular flow conjectures and such kinds of things. And of course in relation to this whole business that I'm describing here, with cross products and so on. But it's a hard problem, so and in general one doesn't know the answer, but it's known for some examples. And these include, for instance, any killing horizons. Boost Hamiltonians for any killing horizons are actually modular operators or modular Hamiltonians of KMS or vacuum states. So So if you have a killing horizon, I think yesterday I wrote it the other way around, but if you have a boost here, and then a killing boost, so it's exactly the thing that we discussed yesterday. Killing boost Hamiltonians R modular or vacuum, also more generally KMS states. We can, quantum field theory, basically the cyclic separating states also use them to define thermal states. So this is just something, okay, that I'm throwing at you. So there's this famous Wichmann, Sunbees, Sewell, ETs, and then a few follow-ups. So Wichmann showed this for Rindler horizons in Minkowski space. So this is actually related to the Unruh effect, this whole thing. And then it was generalized to general killing horizons in the 80s by Sewell. And so, yeah.
For vacuum, you mean vacuum for the entire
Yeah, sorry, yeah. So when we say vacuum, it's the global vacuum. Okay? It's not a regional vacuum, it's the global vacuum. So because here we're talking about, in quantum field theory, the psi states as pure states, they will always be associated with a global universe space because we can't factorize anything else. So, yeah, so states, you should always think of them as global states, whenever I can. And
sorry, and the statement holds for any theory.
Okay.
Any theory
yeah,
means the theory could include a non-renormalizable interaction, blah blah.
Okay, that's a good question.
In general, the notion of the vacuum is non-trivial, I think.
Yeah, for sure. So, well, I guess it has to be renormalizable. Okay, I mean, you can do. No, I mean, you can do this for perturbative gravity, so that's not renormalizable.
But you need a Lorentz invariance.
No, I mean in Minkowski space you have it, but it's also true of general killing horizons in the curved space.
I see.
I mean, you have local Lorentz invariance.
I see.
Locally, but not globally. I mean, the killing boosts, so the boost Hamiltonian, I can add a cosmological horizon, right, a black hole horizon. So I can still define that. I mean, it's really, what you should think of it is, so here, let's call this here, this killing field. I mean, then basically the statement is that H psi, so here it's vacuum, that this is equal to H psi,
Oh,
where this is geometrically defined, and this is defined this way. So that's a really non-trivial relation.
indeed.
So it's very non-trivial. So this here is geometrically defined. So you take your stress energy tensor of this here, you contract it with these killing fields to define Hamiltonian, integrate over, well, in this case, it would be all of some Cauchy slice in space-time. And then the Hamiltonian you get is this one, and you can show it is the modular Hamiltonian.
So in terms of the local field theory, and HC is given by integration of some component of energy momentum tensor, right?
But that's what I'm saying. Yeah. Exactly.
Yeah, right.
So,
But to construct such a composite operator, you have to be careful with the renormalization, you know.
Yeah.
So my curiosity is, and such the modular Hamiltonian could control such UV divergences naturally?
No, not necessarily. No. I mean, that's also related to the type 3 nature of the algebra.
Oh.
Yeah.
I see. So in that sense, that box equation is so non-trivial, right?
It's very non-trivial. Okay. So, but this is exactly the case that we're interested in. Now, the next question is that so this okay? But maybe actually one thing that I can still tell you is a bit of intuition. Why should you expect that the modular, or that the boost Hamiltonian is actually the modular flow, okay, at least an automorphism, and the boost vector fields. I mean, it's a killing flow that leaves the causal wedges invariant, right? So the killing flow lines they remain in the region U dagger. They don't take you out of it. So then you can imagine that if you look at operators that are smeared in the region, they are consistent with that time evolution. So there are initial operators that are that live in AU. Under any time evolution, they should never leave AU. So it must be an automorphism. You look very skeptical. So that's a little bit of an intuition why why boost Hamiltonians give you an automorphism. So something of this kind here, I could add here U for instance, right? So that's because the geometric flow leaves the region invariant, so the corresponding Hamiltonian that generates it must leave the regional algebra invariant. But of course, that's only intuition. That this is then modular flow for the vacuum itself. Much more non-trivial. So now, so when we have that H psi is in the algebra, and so the unfortunate thing, or what makes quantum field theory very difficult, is that for quantum field theory, these modular Hamiltonians are not part of the regional algebra. So in Q of T, for instance, H psi is not part of regional algebra. Of course, it's part of the global. Our bounded functions of it are going to be parts of the global algebra of bounded operators on the global Hilbert space, but they won't be, so we call this here again U and U prime. They're not going to be part of that algebra. And so in particular, what we can do is write it as HU plus HU prime. So, as I mentioned here, okay, I deleted it, but this H psi here, you get by integrating over a full Cauchy slice in space-time. So from that, it's a priori clear that it's not going to be part of the of a regional algebra. But then you could ask the next question: well, can I write it as the sum of pieces where one lies in AU and HU prime lies in its commutant? So classically, we could just take the integral, the space-time integral, and just cut it at the bifurcation surface. But it turns out that you can't do this in the quantum field theory. So, and in particular, these operators are undefined. And what it means is really, you can write them down, you can try to write them down, but then you evaluate them on states in the Hilbert space of the Q of T, and they're just divergent everywhere. They're unbounded. You have basically just no domain for them. So, so that's just no states on which they make sense. And so, and this means in particular that the modular flow Q of t is outer. That's the name. So here it will still be true that this modular flow, it leaves a regional algebra invariant, but it is generated by a Hamiltonian that's not part of the algebra. So that's why it's called outer. It's from the outside. So if the Hamiltonian was part of the algebra, about the functions of it were part of it, then that's called an inner automorphism. And typically in quantum mechanics we consider inner automorphisms, but here in quantum field theory they're outer automorphisms. And this is a defining property of type 3 algebras. So that's any modular flow in type 3 algebras is always outer, necessarily. And okay, the fact that you can't write it in this way also has something to do again with the UV structure on the entangling surface. So if I wanted to cut, this thing here, so I'm cutting again infinitely many degrees of freedom. So I made that heuristic comment yesterday. Quantum many body systems, area law. So for vacuum or ground states, here we're talking about vacuum states. The entanglement is really concentrated around the entangling surface. The quantum field theory of infinitely many degrees of freedom, basically just cutting the Hamiltonian there, just these two divergence. And the Hamiltonian is associated with the vacuum state where we have this infinite divergence in there. So that's kind of a bit of an intuition. It's already almost an hour past. Okay, maybe a crash course on traces in von Neumann algebras. And so, suppose you can write this modular operator that's so basically the exponential of this guy here. Suppose you can write it as something of the following kind, where rho psi is now in AU and rho psi prime is in A prime. By hard dueling, so actually no, I've gone back to quantum field theory now. Okay. That also holds more generally, but but maybe let me just write it like this. So one thing that you can see is that in type 3 algebras, because of what I told you, you can't write H psi, you can't split it into a piece that lives in AU and a piece that lives in AU prime. That's why something like this is impossible in type 3 algebras. Okay? So we have so it's impossible type 3. So whatever I'm going to say, it doesn't hold in that case, but you can now, but anyway, we're interested in type 2 algebras in the end. So you can, for instance, define a trace now by taking your cyclic separating state associated with, so this guy is this one here, and then you can take the inverse of this first one. So I should say, so A, B are in AU. So I just want to give you a bit of intuition of how you would build a trace on that, on such an algebra, a von Neumann algebra, which multiply this here cannot be type 3. And then you write it like this. And now maybe you can also see why I discussed this finite dimensional example, that the cyclic and separating vector in finite dimensions is full rank. So if I did this in finite dimensions, the inverse makes sense for a cyclic separating vector. Okay. So likewise here. I really need a full rank state in order to do this in finite dimensions, but it turns out that for type 2 algebras, you can also do this. You can do a factorization of this, which is of course more sophisticated, but from the finite dimensional analog, you get a bit of intuition why it's maybe possible. So, and really, so I'm debating with myself when I show you that it's cyclic, because it requires a few properties that I haven't shown you. We don't have a lot of time. Do you want to see a little bit why that is cyclic, but I'll have to give you some extra properties that I haven't explained to you before. If anyone wants to see it, otherwise I'll just tell you this. Okay, so I guess then it seems like people are happy with a statement that you can show that is true. So, so yeah, it requires.
The definition of price depends on the psi, just the psi.
Yeah, a priori. Okay. Yeah, that's a good question. So a priori depends on psi. Yeah, here. Yeah, I don't put a psi here. Here I put a psi because I'm using this feature here. Now it turns out what you can already see from this factorization here is nothing stops me from just multiplying rho and rho prime by some constant c, right? Then it doesn't change the modular operator. There's no c inverse will cancel. But then here I will get a 1 over c in here. So I will rescale the definition of the trace. And so, and then it depends on features of the algebra, whether or not I can get rid of this ambiguity, basically. And it turns out for type 2 infinity algebras, you cannot. In type 2 infinity algebras, that's what the cross product leads you to in the end. That's the ambiguity that you're left with at the end, and that's the reason why entropies are only defined really as differences. Because you always have a constant rescaling, and when I take that constant rescaling, I mean, what I should tell you now is, so, okay, let me say a few more words and then I'll say that a bit more. So once you have a trace, you can define density operators. So now I want to have that for some state phi, this density operator is supposed to lie in my algebra. And the way I will define that is by using the trace that I have for and that this is true here. So I have some global state phi for which I want to compute the local density operator, call it rho phi. And what I want is that this here, so and for all a in AU. Okay, so this here is of course well defined. So I have some regional algebra, and I can compute the expectation values of elements in some global state phi, any global state phi. And what I want is that the density operator, so the trace is now only defined on that algebra AU. So I'm looking for an element in the algebra such that it reproduces the expectation values for all A. That's how you can define that. And okay, then you can of course compute the entanglement entropy in the usual way, minus trace rho log rho, and really, if you look at this, then it's just nothing else than phi minus, sorry, this is log rho, so log rho phi And so once you have this, then you can compute entanglement entropies, and okay, it turns out you can do this for anything that's not type 3. And so coming back to the ambiguity that I mentioned, so yeah, you would a priori have this rescaling ambiguity, but it turns out that for type 2 infinity algebras, it's the only ambiguity that is there. So you can write any of the traces really in a form like this here, up to rescaling. And but if you do change the scaling, that changes the trace. It will change the scaling of your row phi's. And then when you compute entropies, okay, you have some constant scaling here, like C times rho phi, and then you factor that out. So then that means the entanglement entropy gets offset by some plus log C. And of course, and that C turns out to be state independent, and when I look at differences of entropies, then that cancels. And okay, so you can also, there's of course a little bit more one can say about it, but let me maybe summarize this in, I wanted to come to the quantum reference frame side of the story still. That gives you a bit of an intuition of how you can think of traces. I should also say, in general, for type 2 algebras, for instance, this is not a Hilbert space trace. So Hilbert space traces, I can take for instance, in a von Neumann algebra, I can always append an identity factor to it on an infinite dimensional Hilbert space. That doesn't change the fact that I have a von Neumann algebra. This trace will still make sense then, but if you take a Hilbert space trace, then you always have an identity on an infinite dimensional Hilbert space, and that just blows up. So it's just to emphasize that that's not a Hilbert space trace in general. Okay, so maybe just the course of von Neumann algebras without any details here. So, okay, I guess you can't read this. So modular Hamiltonians, do they exist? Yes, they exist in all of them. So cyclic separating vectors, all that stuff makes sense. So this can exist in principle in all of these guys. Then this modular flow inner, yes, you can construct counterexamples, but it exists, and here it just never exists. Then traces, they exist, they don't exist in type 3, and so density operators rho, clearly they exist here, they exist here, they don't here, and so entanglement entropies, can compute them here or can't compute them there. And so, and then you can ask, okay, what are, so this here is like standard, if you want to have examples, standard quantum mechanics is always about type 1 algebras. So any finite dimensional Hilbert space, or even also infinite dimensional Hilbert space is usually, we're always dealing with this here. Then type 3 algebras, Q of T algebras, and these are basically gravitational algebras that we use called.
Sorry, just looking at checklist, like I don't see the difference between one type 2.
Well, this exists, this does not exist. So this exists in type 2, but it doesn't in type 2.
Type 1, 2, everything are the same.
Ah, okay, type 1 and 2. Ah, okay. Well, no, I mean, this is a very coarse distinction. Sorry. Yeah, I mean, you can define von Neumann entropy unambiguously in type 1 algebras in quantum mechanics. But as I just explained to you, you cannot in type 2. And in type 2 infinity.
What do you mean by gravitational algebra?
The cross product algebras, for instance. So, for instance, so in the literature now, these cross products that I'm describing, so you address a regional Q of T algebra including gravitons, to these observers. They're often called gravitational algebras. I don't know that.
Linearized loss.
Yeah, it's linear. It's not the most imaginative name, but people have adopted that terminology.
So you mean by QFT algebra, just a
Without
field
gravity.
theory without gravity effect,
Yeah.
something like that.
Or okay, also QG perturbative quantum gravity before addressing. Okay, so so this is really all of what I'm telling you here is really just providing intuition. I'm not doing anything more. But now let's come back to these cross products. So we had yesterday we saw that no, we had for instance in the static patch. So we had mu prime and some gamma here, and then we got this CH as here. I'm gonna put the psi. Yesterday I didn't put it. Okay. And then we had plus P1 minus P2. And then we had AU crossed R. So this cross product. And I just told you that it is given by the von Neumann algebra, which is P1 H psi A. By the way, the signs here, the exponent, don't quote me on that. I'm doing this from the top of my head, so here in this case, maybe it's plus minus here. Which ordering, I forgot. Doesn't matter for what I'm doing here. And so A in AU, S real, and then I put the double commutant there. And so if you remember, I told you yesterday that von Neumann algebras are also characterized by being the double commutants of themselves. And so you can in particular think of the double commutation as closing the algebra. So yesterday I told you that we think about weak closure, so we're adding certain operators in the limits, and that limit turns out to be equivalent for von Neumann algebras to taking the double commutant. So you have some algebra that is generated by these objects, and taking the double commutant of it is basically completing it. And so then we have, okay, these are the relational observables here, and the reorientations. And okay, I guess what I also forgot to say here is that this is AU, and then here in this case, bounded operators. So I guess P1 e to the IS P1 is part of the bounded operators. So maybe it's ideal clocks here. And so it turns out you can prove that the gauge invariant subalgebra of this one here is given by a cross product, when this here is the von Neumann algebra. So now I'm just going to give you a bit of.
Equation you were imposing the gauge constraint.
Sorry?
You were imposing a constraint
Yeah.
even.
Yeah, I mean, so this is an equality here. Wow. Okay, so the cross product you can define in slightly more abstract terms. Let me write it like this, it's isomorphic to this. Okay? But when I represent this on the, because the definition is a bit more abstract, but when I represent this on the Hilbert space that we have here, then you can write it this way. But yeah, the point is here that this here is equal to the full gauge invariant subalgebra of the kinematical algebra formed by this here. And so now I just give you a little bit of an intuition why. So let's call this here A crossed or cross product, just to give you a bit of intuition why this cannot be in type 3 algebra anymore. So, you know, this here is type 3. And so, I mean, so far, that's what we did yesterday, but now the main thing is that this cross-product algebra, it is by construction in the way, and I'm writing it here, gauge invariant. And so in particular, I have that psi cost. So for all S and R, SH psi. So this here is nothing else. So this whole thing here is delta psi IS, right? So this here is the modular flow. Okay, one thing to notice, of course, we had before that this H psi is a modular Hamiltonian for AU. Now we have a bigger algebra, so there's more attached to it. But it turns out you find states in the Hilbert space such that this H psi is still a modular Hamiltonian for this extended algebra. Okay? So maybe I should say that H psi remains, so this was so it was modular for EU, and in particular psi, you know, the vacuum. So in De Sitter it would be the Lutz-Davis vacuum. But you can convince yourself, so I mean, it goes a little bit along the question of how can you check that it is, that you can still have also, you know, a cyclic separating vector, so on. So you can check that this is modular for T1 equals 0 psi. So here I'm taking an unnormalized state. For this algebra here, okay? And so it turns out that the modular Hamiltonian for this state in this algebra here, in this extended algebra, is actually still H psi. So meaning the it is H psi plus 0, where 0 corresponds to the modular part on the of this algebra. So it's still a modular Hamiltonian. And now we will use that this is gauge invariant by construction here. So now conjugation, so if you look at this here, so conjugation by H psi is going to be equal to conjugation by minus P1. P2 will drop out because there's no support on the second Hilbert space here. So this will be equal to e to the I S P1 A crossed e to the minus IS 1. So this here is gauge invariance. So here I'm using, I think clearly by construction you should know now that this is gauge invariant. And then plus that A crossed and P2, they commute, right? Because A crossed has no support on the Hilbert space on which this one is defined. But then what does that tell you? The modular flow is now generated by the clock reorientations. The reorientations are part of the algebra, so the flow is inner. Okay? So it's generated by an element of the algebra. So this thing here is so I've turned modular flow inner. So as I told you here, modular flow is always outer in type 3 algebras, so from this you conclude that it cannot be type 3 algebra. So that it is type 2, and more precisely type 2 infinity is of course a more sophisticated argument than this. But the crux here is that you can now see it's actually the quantum reference frames that turn this into that are responsible for the type conversion. So if I only look at the first part of the algebra here, I mean, it's an automorphism of type 3 algebra, so it is a type 3 algebra if I only looked at this. But it's really the addition of the clock reorientations here that are responsible for this modular flow now being actually equal to being generated by the clock reorientations, and they're part of the algebra. Because they're part of the algebra, that's why the flow is inner, and that's why the this cross product is not the type 3 algebra. And so it's the presence of the quantum reference frames that is responsible for type conversion.
I have two questions. One is for the like a T. You said that it's modular for TA equals 0 tensor. Yes.
T1. Yeah.
T1 equals. And do you need to restrict T1 equals 0, or I thought it's just modular for any T?
I think you needed T1 equals 0. No, actually, maybe. No, actually, I think yeah, maybe. Okay, off the top of my head, I'm not quite sure, but I think yeah, maybe you could take some other T because really, by the clock reorientations, you run through the full basis. So yeah. No, actually, I think yeah, you could take any T really because if you take the clock reorientations and you just act on this here, you generate any T states, so you get a full basis on zero space.
Okay. And another question is,
Okay. Sorry, wait a minute. Maybe because that is kind of going in the direction of being cyclic, so you would still have to check the separating condition, and then off the top of my head, I would probably make a mistake. But anyway, this one can check it works. Yeah, for the cyclic part, you could take any T state, but for the separating part.
Yeah,
it would probably take a few minutes to check that now.
Yeah, and this discussion, making turning the type 3 to type 2 sounds like it also works for non-gravitating case. So what's special about okay, so Hamiltonian constraint comes into the discussion, but like for Orion quantum system, let's say we just say there is an energy conservation, and we impose this kind of Hamiltonian constraint in a sense.
But yeah, you wouldn't. I mean, the crux is of course that you have to go to. I mean, you have to pose an Hamiltonian constraint in order to get this here, and that is a consequence of gravity, right? So, and the thing is, of course, that it is related to diffeomorphism. By it is an example where the modular flow is geometric and it corresponds to diffeomorphism. So I should be posing it as a constraint. So that's why I should look at these gauge invariant algebras. So that's why I'm naturally led to this. But so you can of course also you can build cross products also in standard gauge theories. But then you wouldn't be crossing with something like R, but actually something that maybe a compact group like U1 or something in QED. And that turns out, I mean, that will not be a modular flow actually. Okay. So the crux here is that this is it's a modular, so-called modular cross product. So I'm crossing the algebra with the modular flow in it. But a cross product is much more generally defined. So I can have, I just need a group action of the group on that algebra. And in gauge theories, I will have that. I can build cross products in gauge theories, but the point is there's no modular operator there. And so this whole discussion about the generator of that flow being inner or outer or so that I've described here will not apply in that case.
Actually, I was asking a pretty naive thing. So like let's say we consider just an Orion quantum field theory without any gravity, and but
Also,
like
you just want to impose the
yeah,
constraint
we
anyway.
just put the clock system and just say there is a global symmetry that conserves energy. And
Yeah, I mean, in principle, I mean, you would have to have a good justification for doing so, because the thing is that, of course, so in standard QFT, for instance, also in the zeta, I mean, the kinematical Hilbert space is the physical Hilbert space, right? And now the point is, when we build the physical Hilbert space, it's not a subspace of that. So you would say, you know, the kinematic Hilbert space is the right one that describes whatever scattering and so on in the zeta space. So you would have to have a very good reason why you want to go away from that Hilbert space to a different Hilbert space.
I see.
So technically, nothing would stop you from doing this. Of course, you could in principle do this, but you don't really have a reason to do so.
I see.
And here, it's important that it's not going to be a subspace of that.
In this discussion, was it
Yeah.
essential to introduce one-dimensional additional degrees of freedom like can you introduce more general quantum mechanics?
Yeah, you can. So it's just that, okay, CLPW did it this way. They explained why deparametrizing the other isometries doesn't change the conclusion that you have a type conversion. So the type conversion really comes from the modular flow, from this modular gauge symmetry. And the other isometries are not modular flows. Okay, because the thing is that the remaining isometries, because you're looking at a subregion, really, they have to leave a static patch invariant, and they're all compact groups. So it's some SO D-1 or whatever. And then, you know, this modular flow is always a translation group. Okay? So it's always a non-compact group. And you know, the compact group doesn't generate this modular flow.
I was imagining like you explained a very simple example, like a particle moving along in one direction, and in that case, you pick one particle at some position as a quantum reference frame. Can you do that? Can you do the similar thing for the QFT case? Not additionally introducing the clock degree.
So what do you mean?
So-
To do what? So to not introduce a clock degree reference? Or to introduce a clock degree reference on top of it? Is that what you're asking?
Right.
Well, in principle you could, but then you're of course changing the system, right?
Right.
So, I mean, and that's also what's happening here, right? So we're going from a pure QFT description to QFT plus additional degrees
Yeah,
of
but
freedom.
I think it's a little bit artificial compared to the example you made.
This one here is more artificial, or?
Yeah.
Yeah. I mean, okay. So this here was, I think, more. You know, it was the first time that this was noted, and okay, well, I think most people would agree that this is a bit of a. You know, you should view it as a toy model, really, right?
I think it would be nice to if you can introduce some quantum reference frame within the system.
Yeah, you can. So so here, I mean, you can of course always think that. Okay. I mean, so the way you should view this here is from the point of view of the full quantum field theory or quantum gravity theory, is that you're in some sort of subspace where the degrees of freedom making up the observers at a very special state, such that this description makes sense. So you should really view it as a kind of special subspace of your full quantum gravity theory. But now the thing is that so these ideas have been generalized. So, for instance, there's some works by Jeff Pennington and I forgot his co-author, and by Gautam Satychandran and other guys in Princeton, Jonah Kuhn, Leuthäuser, where they actually use, where they don't insert clocks by hand, but they extract them from the inflaton field, for instance. So you have, so they extract it from the quantum field degrees of freedom. And the conclusion is basically the same. So certain modes from the inflaton field, slow roll inflation, they will basically give you something like this. Okay. And then Anthony Speranza, okay. In some of the earlier works, then they claimed it is not a cross product, but then Anthony Speranza recently showed that actually it is a cross product. So really, this should be more viewed as a kind of simple qualitative example, that there's some kind of type conversion happening when you dress regional degrees of freedom to something else. And the point being really, okay, this crowd does really call it quantum reference frames, but also what Pennington and all these guys did, what they extracted from the quantum fields to deparameterize the modular flow, all of these are quantum reference frames. So they're just more sophisticated quantum reference frames. So this here is of course the simplest possible one I can choose. Okay.
What happens if chromes are not divided?
If they, yeah. So let me come to that now. So can I have another 5, maybe 10 minutes? Because then I will wrap this topic, and then after the break we can move to gauge theories. So. So I still think it's a nice example because it's very explicit, you know. Okay. I should still tell you a little bit more. Yeah, okay. Maybe I'm gonna include the non-ideal case directly what I'm gonna discuss now. So CLPW. Chandrasekhar, Longo, Pennington, Witten. So they followed this path of this co-invariant method that I briefly described yesterday. So defining physical states in terms of these equivalence classes. And so to represent co-invariants, they defined a map. And they call it something like T. So I'm using our notation from the kinematic Hilbert space. So okay, I guess I should say Hkin is H Q of T. So you know where H psi lives on, then just call it H1 and H2. So really, a priori, in the way in which I described it, H1, H2 will just be 2 L2s of R. Then, I'm just debating with how I'm going to write this. Let me just write it. Let me just call it HFIS. So they called it a representation of covariance. And the map that they wrote down, so it has to be well defined on these equivalence classes that I described yesterday. And it's given by psi, so psi kinetical. Psi kin. And yeah, here put a T, and I put a T2 here. So this will be the T2, the clock states from the second one here. So the complementary observer. And then IT H psi plus 1. So I'm basically translating what they wrote down into our language. And so they wrote it as something like psi of t, but this psi of t that they wrote down is really this guy here. Okay, so you're throwing in the second clock and you're conditioning on it. But then, so this is really what they wrote down, and they showed, gives you a good description of covariance, but now should be clear to you what's happening. So it's T2 equals 0, so I can use the covariance of these clock states now. So I'm just going to use that T2 is going to be P2 equals 0, then e to the I P2 T2. So that's just the covariance of these clock states. So I can take this out. So what do we have then? dt. Sorry, here I should have a minus. Sorry. And so here you will get e to the minus it ch, and then cycle. Is that clear? So I'm just using the covariance of the clock states here to pull out the t equals 0 state for the second clock. So it's for 2. And then here I combine this this factor. So this here is an operator, this not. Sorry. It's sorry, I'm making a mistake here. This should be the 2 label should be here. Sorry about that. Should be this, like this. That's not T2 here. So then I can combine this factor with this one, and then using that there's a relative sign here, I can rewrite it as a constraint. And so this is, of course, nothing else than this pi pn. That's the page-Wooders reduction map here. So then you see it's R2 of 0 pi pn so in this loose the sloppy notation that I've done so far, there's nothing else than R2 of 0 of psi. So now you can see that what CLPW have done to describe physical states is equivalent to the page-Wooders reduction, so it's actually equivalent to the perspective neutral approach. So in this so we use this then to write down the slogan PW equals CLPW. So a bit like ER equals EPR, but it's a more non-trivial equation because ER equals EPR. The E and R are the same on both, but this PW and that PW are not the same. So so CL is a non-trivial operation there. And it's equivalent to the PN framework. So that's why I mean, of course they didn't know that, but their description of physical states. And also, I mean, here it should be clear to you now that this is really just it's part of the perspective neutral approach. It's the relation of observables, frame orientations, and then physical states are described using. Using the, so I was hesitating here a little bit to call this HFIS because at the end of the day it's a gauge fixed description of HFIS. I don't remember what they called it, but it's of course correct that it gives you a description of gauge invariant states. And anyway, so you see, okay, so when they wrote this T-map down, they wrote it down for ideal clocks. Okay, but you immediately see that in order for this to be true, I don't need ideal clocks. All I need is this covariance condition here, and that's all. So that's why, so this construction holds also for non-ideal clocks. And now the next step is to actually take.
So you can get type to algebra.
Yes. Well, actually, they become even nicer. So this here is. I mean, here I just gave you intuition that it cannot be type 3. for ideal clocks, so the cross product is always type 2 infinity, which means not every state is a tracial state, and this ambiguity in defining the trace that I mentioned you can't resolve. That's why only entropy differences are well defined. But now it turns out that as soon as you put a lower bound on the clock energy, so I explained, in previous lectures how to handle that with these covariant POVMs. That actually leads to projection of the cross product algebra to a subalgebra. And that subalgebra is a so-called type 2-1 algebra. And the type 2-1 algebra is one where every state or every operator is actually trace class. In particular, the identity is trace class. It means you can normalize the trace by the identity. You just set it equal to 1. And then in this way, you get an unambiguous definition of entropies. Of course, you're setting a scale, and here the subart counter, the thing that is a bit different to standard descriptions of Hermann entropies is that when you set trace identity equals 1, it means that the maximally entangled state, basically you have a maximal entropy state in type 2-1 algebras. It's the identity, and that one has fundamental entropy 0. It means all other states have fundamental entropy that's negative.
Just in the definition here, I say H modular.
Yeah, so this is H psi plus P1. Yeah. Yeah, so that's, but describing this takes too much time, so I'm just going to say that here, and I still wanted to connect it briefly, at least qualitatively, with subsystem relativity. I won't explain that in detail in this lunch break, but just to wrap this up. So yeah, so A crossed is type 2 infinity. So so only delta SE unambiguous. So for non-ideal clocks, with lower bound on HC, we get, you can view this basically, you get a, let's say we take clock 1, and then you can just put, for instance, a theta function of P1 in there. Okay. So that's a projector. And in this way, you cut off the negative energy. So this is an example that they give in that case. And now, when you think about this here, this is a bounded operator. It's a bounded function of P1. So that means this pi C1 is actually contained, and it's gauge invariant. Of course, by construction, it commutes with the constraint, and it's bounded, so it's actually contained in the algebra. Okay. So this is actually contained in A crossed. So then you can actually go from A crossed to pi C1 A crossed pi C1. So that would be the subalgebra. So it's a subalgebra of the cross product algebra that would correspond to a lower bound on P1. And this one is type 2-1. So SEE well defined. And importantly, it has a maximal entropy state. And that's also then connected to properties of the zither space that really the maximum entropy state, like the initial or final states, that corresponds to basically all the degrees of freedom in a static patch having gone out of the cosmological horizon, and then there's nothing left in the region. Okay, so it turns out you can make this, you just need a bound on a lower bound on the clock. Doesn't have to be 0, it can be something else. So here what I've described so far is really just essentially a quantum reference frame interpretation.
Excuse me.
Yeah.
Is it enough to put the lower bound on only B1? Not necessarily.
Well, yeah, so here it is enough to say that the cross product algebra describing this region is type 2-1. I don't need to say anything about this.
Excuse me.
Yeah.
How about more general clock? I mean, discrete spectrum.
Oh yeah, so we discussed that in one of our papers. So for instance, U1 clocks. So some periodic clocks. So it becomes more complicated in that case. And actually, I forgot what our conclusion was. I don't think you get generically a type 2 algebra in that case. So I think you get something more complicated. So yeah, so far it's really, I'm just giving you a quantum reference frame interpretation of what these guys have done. The final thing I just want to say in words now, basically, I'm not going to really write this down. But the point is, at the end of the day, that these entanglement entropies that you compute using the cross product are actually relative to the quantum reference frame, really. Okay. One thing that I forgot to say is, this here is still basically a kinematic definition of gauge invariant operators, right? But I still need to do, so this is basically at the level of what I call O without a twiddle. But now we want to actually represent it on the physical Hilbert space, so you would have to take your cross product and represent it on the physical Hilbert space, and in particular then reduce it using this T-map to the image here. So it won't shock you from what you've seen that, okay, you just get the descriptions, these gauge fixed reduced descriptions that I've already described in the Page-Wooders construction. So the subsystem relativity will in particular apply now. So we can now consider any region U, and so we have our algebra AU. And so here in our case, okay, there's one observer, for instance, or in their case, there's just one observer, one clock. But you can, in principle, of course, populate it with many more. You can add further quantum reference frames. So if you add one observer, why not add more? We can add additional ones. So the reason I want to add them to the same region is that then, I guess I haven't said that yet, but here in this case, if we translate that to what we did before, basically U is now the system, okay? So the system that's supposed to be described relative to the quantum reference frame. So I can't use that second quantum reference frame over here because that one looks at a different system. Okay, so we have to slightly extend what we did before. So if we want to have the subsystem relativity or describe that thing, we have to have two quantum reference frames that describe the same system. Okay? So that's why I want to add additional quantum reference frames in the same region. And then you can run a similar kind of business. It turns out to be significantly more complicated. So just writing down basic gauge invariant algebras, that's not hard. I mean, that's very simple from what I've told you. But I haven't told you how you compute the density operators. So the density operator, I just told you how to define a trace. In principle, that idea still holds in when you add additional quantum reference frames, but it turns out that when you add additional quantum reference frames generically, the Hilbert space no longer contains cyclic separating states from that algebra. So by that I mean the original kinematic Hilbert space or the physical Hilbert space. But then you can make use of the fact that, okay, there's still type 2 algebras. That only means that trace is defined up to a constant. And I can just define them on any Hilbert space in which I can represent that algebra. To define a trace, that's what you can do. Then you have to use sophisticated techniques to map it back to the physical Hilbert space, blah, blah, blah. You can all do that. So, but it's a much more sophisticated construction than the previous ones. But then you can show that you can actually compute reduced density operators for for regions, also in that case, after a lot of exercise, and also for subalgebras describing maybe only some of the observers inside the region. But in any case, the upshot there is that if you now look at, again, the total perspective neutral algebra for the full Hilbert space, okay, then you can have, for instance, again, that this here may be AU relative to clock 1, and this here is then AU relative to clock, say, 2, a second one, or another one, and here represented on the physical Hilbert space. Then again, you will find that they overlap exactly in AU, but now that is gauge invariant, the gauge invariant part. So that's the same argument, well, I never really explained that in detail, I just gave you intuition, but the same thing applies here. But okay, represented on HPN. But then I told you yesterday that the gauge invariant algebra of the Q of t is trivial. Okay, so in this case, this is a case where the overlap is as trivial as it gets, it's just the identity component. So there's really, they don't share anything in common, these two algebras. Relational algebras, so there's the strongest form of subsystem relativity that you can have. However, you should keep in mind that this does mean that they're independent subsystems, because it turns out the two algebras don't commute. So if you do a measurement here, it will affect what happens there. But anyway, you have a very extreme form of subsystem relativity, and that shouldn't surprise you then that I can find global states in the Hilbert space for the global theory, so global Cauchy slice, in the global Hilbert space containing all the degrees of freedom, so the perspective neutral one, there's many states in there, such that when I compute the density operators relative to clock 1 or clock 2, then I evaluate the entanglement entropies associated with this or that algebra. So what one clock or what the other clock sees as the Q of t degrees of freedom, the region then in general will be different. So in general, you'll have that. Let me just write it as u relative to some phi C1 is not equal to general, let me say generically. I mean, there are of course counterexamples, but so generically for phi in HPN, you will have that. So there's a subsystem relativity. And so the regional gravitational entropies are QRF, or observer independent if you want to use so that's the final thing I wanted to say about this. So, okay, sorry for going very far over. Sorry?
So the gravitational entropy is just the area top plus